We'll continue with the discussion of the properties of Fourier series. So we saw that earlier what is a Fourier series and how to decompose any given periodic signal in terms of Fourier series. So I'll write down the expression just for sake of completion. So let's say there is a signal z of t, and we said that we can decompose that in terms of the sinusoids, so which are nothing but our eigenfunctions, and we'll take a particular fundamental frequency and then decompose any given signal in terms of its harmonics, and these are the coefficients, basically the component of the sinusoid that is present inside this periodic signal. And how do we compute these coefficients? The coefficients are computed simply by taking the inner product over one period. Okay, inner product, basically you project the sinusoid onto the given signal, and this projection is done over one period, and then you just normalized the power of the sinusoid in that one period. So this is Fourier series representation. So remember, we said that this Fourier series representation is just like representing a given signal in a different domain. So you take the signal in time domain. So basically what you do is you have some signal which you can visualize in the time domain, something like this. Remember, it's periodic, so something like this. So this is one way of visualizing or representing a signal. There is another way where you just visualize or represent the signal in terms of the amount of frequency component that is present. All you do is just plot these coefficients. So if you plot these coefficients, you get something like this. So at k equal to 0, you have something, k is equal to 1, you have something, k equal to 3, something like this. Okay. So this is one way of visualizing the same signal. So it's not two different things, it's the same thing, but from a different perspective. So remember, we were talking about an analogy in terms of currency. So you can see the same amount in Indian rupees or in US dollars, but it's the same thing. And what we are going to see now is something which is going to reinforce this. So the amount of energy that is present in any of the representation is still the same. So energy is similar to the length of the signal, but of course we know the signal is extending from minus infinity to infinity. So to capture this notion of length, we define what is known as this energy. It's not really equal to the physical energy that we usually talk about. So of course when you have the same vector, you cannot have different lengths in different domain, right? It has to be the same length. That's what we are going to say here through Parseval's theorem. So it's the same vector or it's the same signal. So you cannot have different notions of energy in different representation. However you represent it, how much ever amount of money you have in whatever currency you represented, the value should be the same, right? So that's what this says. So the energy content should be the same, either you represent it in time domain or you represent it in the Fourier series coefficients. So the energy content is always the same. So that's what we mean by the Parseval's theorem here, which states that you compute the energy of the signal in one period. So this is how you compute the energy of the signal in one period, right? So if you compute this, whatever that is present here should be exactly the same as energy that you get from your Fourier series representation, right? So if you try and compute this equation, what is this equation? This is the energy of the signal in one period. And what do we get here? So this is nothing but, you can just plug in this representation here, summation ak e power j omega t dt, this whole. But because these are all orthogonal, the summation, the square of the summation is equal to the summation of the square. That is true only because of orthogonality. Once again, orthogonality comes to our rescue. It simplifies this expression. Okay. So we are able to move from this step to this step purely because these signals are orthogonal. Otherwise, this is not true. Okay. All right. So now this is orthogonal and this is just a phasor. The phasor energy has to be just 1. Okay. So which means what we have. So we have summation okay, integral 1 dt over a period t. So if you are integrating just a constant signal over a period t, then it's like computing the area of a rectangle whose height is 1 and width is t. So this value is going to be t. Okay, that's it. So this is what Parseval's theorem that states that. So Parseval's theorem, remember earlier we saw a general notion of Parseval's theorem. You just take the general notion and then compute the energy within one period, and that's it. So if you compute the energy within one period, the general Parseval's theorem that we had earlier, this is the general Parseval's theorem that we had earlier, right? That the energy in one domain is still equal to the energy in the other domain because it's the same signal, and this is the energy in different domains. And you just substitute for the energy of the bases. What are the bases here? The bases are the complex sinusoids, which are the eigenfunctions, and the energy of the bases in one period is capital T, and that's it. So you get the Parseval's theorem relationship for Fourier series representation. That is, the choice of the basis here is the harmonics that we have chosen, harmonics of a fundamental frequency. So this gives us the Parseval's theorem for Fourier series representation of periodic signals. So the interesting thing is, we know that the periodic signals are all power signals, which means their energy is infinite. So we have still computed only the energy in one period, but of course we know that the period keeps repeating itself again and again. So typically when we talk about these periodic signals, we talk only in terms of the power of the signals, not in terms of the energy, because energy is infinity and we talk only in terms of power. So can we somehow quantify the power here? Yes, we can, because it turns out to be easier to quantify the power. So once again, if you remember the relationship between power and energy for periodic signal, we said that the power of the periodic signal, which is equal to limit t tends to infinity 1 by t minus t by 2 plus t by 2. So this is the power of the periodic signal, or any signal for that matter. Basically, you take the average energy and the period over which you keep averaging, you keep increasing. For a periodic signal, we already proved this. You can go back and check in your lectures, older lectures. We proved that this is nothing but the average of the energy of the signal that is present in one period. So if you compute the energy of a periodic signal in one period and find its time average, that's exactly equal to its power. Okay, and from this Parseval's relationship, we know that this is nothing but 1 by t times t of summation over all the Fourier series coefficients squared. In other words, this is what we have. So we have a very nice relationship between the power of the signal and the Fourier series coefficient for periodic signals. So the power of the signal is essentially nothing but the sum of the squared magnitudes of the Fourier series coefficients. Okay, and this makes sense because the power that is present in the eigenfunctions, which are our bases that we have chosen here, that is equal to 1, because their energy in one period is t. So their average energy, which is the power, is equal to 1. And remember the same thing that we talked about earlier, when we have orthogonal signals, the powers add up. So in this case, the powers completely just add up. So the power of one component that is present here is nothing but the squared magnitude of the Fourier series, corresponding Fourier series coefficient, and that's exactly what we get here. So whatever we read earlier, whatever we studied earlier about the properties of the power and energy of periodic signals and orthogonal signals, they help us here to do this analysis and then say that, okay, if I know the power in the time domain and if I compute the power in the frequency domain or the Fourier series domain, I know that they have to be equal. So that's what it says. So the power in the time domain, if I compute the power in the time domain, whatever signal that I observe, and I try to compute the power in the Fourier series representation, they have to be equal. So if I know this in the Fourier domain, I know what will be the power in the time domain and vice versa. So from one I can compute the other. So this relationship often helps us in practice to compute the power of a particular frequency component. Now let's say I have a signal that is, I have an audio signal that I have recorded. let's say it is an audio signal which is a recording of let us say a bass guitar and something which is like a high frequency violin, let's say. Now, if I want to know how much of the power of the signal is in the violin's music and how much of that is present in bass guitar, all I have to do is I have to separate out these two frequency components. I know the bass guitar will have low frequency, I know that the violin will have high frequency. So, I just have to compute these coefficients for high frequency. So, from this computation I can say that, let's say, for k greater than some 100, which corresponds to the high frequency component, I can say that the summation of all these Fourier series coefficients for k greater than 100, they all correspond to the power that is coming through the violin's music, and anything that is less than that comes from the power that corresponds to the bass guitar's music. So, with this we are able to quantify that in the given signal the contribution of one particular frequency component or one particular instrument is this much, and the contribution of the percentage of amount of power from one particular device or one particular frequency is this much. So, we are able to separate out and say that how much a particular frequency is contributing to our actual signal. So, if you observe the time domain, we won't be able to tell that okay, this frequency or this particular device is contributing so much to our time domain observation. That information is lost in the time domain, whereas when we represent in the frequency domain, this information is evident. So, not only does the Fourier series representation help us simplify convolution, but it also gives some nice insights like this.